Hello everyone, this is the paper Fisher Discriminant Triplet and Contrastive Losses for Training Siamese Networks. I'm Benjamin Kojok, and my co-authors are Milad Sikarudi, Sopan Shafi, Hamid Tiesush, Fakhri Karay, and Mark Crowley. This is a joint work by the Department of Electrical and Computer Engineering and Kimia Lab at the University of Waterloo. Size network is a combination of two or three subnetworks which share their weights, so their weights are equal. And there are two popular loss functions for training Siamese networks, which are triplet loss and contrastive loss. In triplet loss, we have a triplets of anchor, neighbor, and distant, or anchor positive and negatives, where anchor and neighbor belong to the same class or are similar, and anchor and distant belong to different classes or are dissimilar. And we want to train an embedding space which embeds anchor and neighbors close to each other, but embeds anchor and distant far away from each other. So the classes, the samples of each class fall close to one another, but the samples of different classes fall away. And in contrastive loss, once we consider the pairs of either anchor neighbor or anchor and distant, but for the pair of anchor neighbor, they should fall, pulled together, but for the pair of anchor distant, they should be pulled away from each other. The FDA, Fisher Discriminant Analysis, or FDA method, is a linear subspace learning method which is based on generalized eigenvalue problem. And it is an embedding subspace which decreases the variance of each class or the intra-class variance, and increases the variance between the classes or the inter-class variance. We see that both Siamese network and Fisher discriminant analysis embed the data so that the samples of each class collapse close together, and the samples of classes, different classes, are embedded far fall far away from each other in the embedding space. You can see there is a similarity between Siamese network and Fisher discriminant analysis, and this motivated us to propose Fisher losses for Siamese networks. Assume that we have C classes, and the samples of the kth class are denoted by the superscript k in parentheses, and the dimensionality of data we denoted by d, dimensionality of subspace we denoted by p, where p is less than or equal to d. Consider a projection matrix to the subspace denoted by u, and it can be shown that variance of projected data is U transpose SU because of the quadratic characteristic of variance. And within scatter and between scatter, or the intra-class and inter-class variances, are denoted by SW and SB respectively. And you can see that we can have different types of Fisher criterion which we want to maximize. The most famous one is trace of U transpose SBU over trace of U transpose SWU. The other one is SW inverse SB, which is the solution of a generalized eigenvalue problem. And it can also be trace of U transpose SBU minus trace of U transpose SWU, which is the Lagrange relaxation of the optimization of, similar to the Lagrange relaxation of the optimization of FDA. If we maximize the Fisher criterion trace of U transpose SBU over trace of U transpose SWU, this optimization, this is a Rayleigh-Ritz coefficient, and this optimization can be recast to maximize trace of U transpose SBU subject to U transpose SWU equals a constant. The Lagrangian of it, if we write the Lagrangian of this optimization problem and take derivative with respect to the variable u, and we set it to 0, we will come up with a generalized eigenvalue problem, SBSW, where the eigenvectors of this generalized eigenvalue problem span the subspace of FDA. Let's see the triplet loss in theory. You can see that we have assumed that the embedding of anchor is fxa, embedding of neighbor is fxn, and the embedding of distant is fxd. So we can have something like this, where the bracket with plus is the standard hinge loss, and we have a margin alpha which is positive, and we want the distance of anchor and distant be at least alpha away from the distance of anchor and neighbor. Here we also see contrastive loss in theory. You can see that it's assumed that y is 0 and 1 is 0 when the pair x1 and x2 is anchor neighbor, and it is 1 where this pair is anchor distant. So we can introduce contrastive loss as this. One of these two terms in the contrastive loss is becomes 0 and the other one becomes 1, depending on whether we see if we take anchor neighbor pair or anchor distant, and the margin is still alpha. In our methodology, we have a network structure like as you see in this figure. We have a backbone neural network, which can be any neural network, either fully connected or convolutional. And we also add a fully connected layer at the end, whose weights are denoted by U, which can be seen as a projection matrix. We consider the subspace before the projection. We name it latent space, which has Q neurons, and let the final embedding space be feature space, whose dimensionality is P, and P is less than or equal to Q. The idea is that we train the backbone neural network where the latent space tries to find a good discriminative space, but it's not still yet very good. By projection to the feature space, we fine-tune the embedding space in order to discriminate the classes better. And consider the triplet XA, XN, XD. We denote the latent embedding of these by O, AON, and OD, and the final embedding of those by FXA, FXN, and FXD. Similarly, we have something like that for the pairs, which will be used for contrastive loss. Here we propose Fisher Discriminant Triplet or FDT loss inspired by the Triplet loss. We want to maximize the Fisher criterion, but in neural networks we usually minimize the objective function. So we minimize minus Fisher criterion, which is trace of U transpose SWU minus trace of U transpose SBU. But we see there is a problem here, because in order to minimize this objective function, the embedding space tries to explode so the between scatters improve, and the loss functions goes to minus infinity. In order to prevent this, we penalize the total scatter of the embedding by the regularization parameter eta, which is between 0 and 1. And in the literature we see that total scatter equals between scatter plus within scatter. So if we put it in the objective function and we solve it out, we'll come up with 2 minus lambda trace of U transpose SWU minus lambda trace of U transpose SBU plus a margin. And if we put it in the standard hinge loss, we'll have FDT loss. It is recommended that lambda to be a small value in order to penalize the between scatter more. Now we introduce define the scatters in the FDT loss. So as you see in the network structure, we define the within and between scatter as the scatters in the latent space, because it can be seen as the input for the Fisher discriminant analysis somehow as the last layer. So we define OW and OB as OA minus ON for the whole batch. We denote the batch size by small b. And we consider the within and between scatter as defined here in the latent space. But there is a problem. The ranks of intra and interclass scatters are mean of Q and B minus 1. And the rank of the Fisher discriminant analysis SW inverse SB is B minus 1, because we usually the batch size is smaller than Q, the number of neurons in latent space. So in order to make it full rank, we slightly strengthen the main diagonal of SW and SB by mu W and mu B as small numbers. Now we propose Fisher Discriminant Contrastive Loss, or FDC loss, inspired by Contrastive Loss. Recall what we found for Fisher Discriminant Triplet Loss, and by modifying it, we will have FDC loss, slightly modifying it, as and this modification can be seen as by comparing triplet loss and standard triplet loss and standard contrastive loss. And but the between and within the scatters here are slightly different. So we define within and between a scatter as the scatter in the latent space again, but for the pairs rather than triplets. Now we consider y as 0 and 1 when the pairs x1 and x2 is anchor neighbor or anchor distant respectively, and we define the within and between scatter in the latent space depending on whether they are anchor neighbor to be in within scatter or anchor distant to be in between scatter. And we define the Fisher Discriminant Contrastive Loss as you can see here. For experiments, we used 3 datasets, which are MNIST dataset with 28 by 28 pixels. We created 500 triplets to test the proposed loss functions with a small number of triplets. For a large number of triplets, we tested on 2 publicly available histopathology datasets, which are CRC datasets and TCGA. CRC dataset includes several tissue types, which are shown. Some of them are shown in this figure. We split it into train and test sets with 60 and 40% portions, and we extracted 22,000 triplets from the train set. We also used TCGA dataset, which we extracted 22,000 triplets out of it, and we used 3 organs, prostate, gastro, and lung organs in this dataset. Here we visualize the embedding of triplet loss, FDT loss, contrastive loss, and FDC loss in order to compare those for both training and test sets. And as you can see, the FDT loss has better embedding than triplet loss, and FDC loss but FDC loss and contrastive loss almost have equivalently good embeddings. So this shows that at least for MNIST dataset, the proposed loss functions are working very well. In the next slides, we see for the histopathology data, they work well too. Here, once we train the Siamese network only using the CRC dataset, and we embed the CRC dataset again, or we train it by TCGA dataset and we embedded CRC dataset in the second row. And as you can see, all the proposed loss functions work very well to separate these tissues, especially the tissues which are visually far away from the other tissues have been embedded far away in the embedded space as expected. Here we apply one nearest neighbor search for different loss functions in the embedded space, and as you can see, we usually outperform triplet and contrastive loss functions, and we also show the impact of lambda in our loss functions. As you can see, lambda equals 0.1 is usually working well enough. If it's too small, it emphasizes a lot on the total scatter and does not discriminate the classes very well. If it is too large, the embedding space explodes. So 0.1 works usually well. Here in the second column, we visualize the embedding of latent space, and in the first column we visualize the embedding of feature space. And as you can see, feature space has more fine-tuned embedding than the latent space because of that projection that we had. Thank you for your notice.